right, let's look at energy analysis flow diagrams with LOL charts. The circle is the system, the L's represent bar charts for initial energies and final energies. And we get to choose what those are in moments in time. So let's take a look at an example. Mr. Q pushes a bunch of students in a cart across the room. These probably are unruly students. They probably don't want to be pushed in a cart, but so be it. And we're going to do this from rest. So the first thing we need to do is identify the system. And one of the best ways to do that is by drawing a picture. So here's the first moment that we're going to look at. Mr. Q is pushing the cart with some students in there. Let's put some legs on Mr. Q. That's probably a good idea. And they're not quite moving yet, so we're going to say it's from rest, which means speed equals 0. So we're going to put a variable v equals 0. That's a quick way of identifying how fast they're going. There's our floor, and this is our event 1. And we go ahead and think about it. This is the moment when Mr. Q starts to push the cart. We're going to be focusing on moments in time. So later on, let's pick a different moment in time. Maybe Mr. Q is running really fast, the cart's really speedy here, and now the kids, I don't know, they don't look like they're unruly anymore. They look like they're actually having fun. So if we want to say the speed is way fast in the equation form without putting numbers, we can use this special symbol, which means way greater than. So we can say the speed is way greater than 0. So this event will be when, let's say, Mr. Q reaches maximum speed, which also means the cart reaches maximum speed. We could have picked any moment in time, but we're going to pick that one to make things a little bit easier. We can tell he's going fast because his hat flies off. Of course. All right, so we have event 1 and event 2. Let's take a look at the system. So what's our system? Let's go ahead and do the words. Mr. Q, cart of students, floor, and the earth field. Let's put in the interactions. Mr. Q is touching the cart, the floor, is being pulled by the earth, and so on. So let's identify the system. We have a couple things we can do. First test, let's say everything's the system. So let's do our LOL chart. Okay, anyway, event 1, event 2. Let's remind ourselves really quick what they are. Starts pushing and reaches maximum speed. And let's put the system in there. And that's our system boundary. That circle represents our system boundary. Pretty cool, huh? The total change in energy is 0. So where do we start? Well, Mr. Q's pushing, so that's probably chemical potential energy. And we put 5 blocks there, so we're going to have to put 5 blocks over here because the total change is 0. So we cannot increase, cannot decrease. So we decided to put 2 categories, maybe some thermal and some kinetic. So we write that as EK. We could arrange that so thermal is more than kinetic energy. It really doesn't matter. We could have some chemical left. We could just do a bunch of stuff as long as it totals up to 5. Maybe there was no friction. It was all kinetic. Maybe there was only 4 blocks. If that's the case, then we have to deal with 4 blocks on the other side. Whatever. So let's go ahead and make an equation out of this. We take our blocks with our events separated by an equal sign. So we have chemical potential energy initially becomes kinetic energy and thermal energy at the end, or final. So we can also say 1 for the first event and 2 for the second event, just to kind of keep things going. But what if I wasn't inside the system? What if Mr. Q wasn't part of the system? So here's our test 2, where everything except Mr. Q. So we circle everything but Mr. Q. Notice there's some interactions that go across the system boundary. So now we have Mr. Q without the system in there. So the actual energy that started is now 0. And we end up with the same results we had before, kinetic energy and thermal energy in the second event. So that didn't change. So where does it come from? Well, Mr. Q, of course, but across the system boundary. And this is what we call working. That's where the energy is coming from. It's coming from outside the system through a force or an interaction. We call that working. So let's go ahead and look at what the equation becomes now. So no internal energy, no storage mode account at all. So initial energy is 0. So we have some W, some work, and it's going to become the kinetic and thermal energy we saw before. Notice we don't really have to put a number on the work. We're just going to put the numbers on the other ones. So our first test was all internal energies, all storage accounts. So that became that equation. And test 2 was outside the system, so we have work happening, and that ends the same way. So depending on what we need, we do it either way. In this lab, we're going to be working with a spring on a hanger, and we have like a paper clip here to kind of help us put on these washers. For all intents and purposes, these washers are about the same mass. Okay, so what you're going to do is we're going to be looking, I just want you to observe this next thing and see what you can pick out. What things can we measure? What are we trying to do? Remember, this unit's on energy. So I want you to think about the system. I want you to think about what's happening as I hang each of these on here. So taking a look at that, we see that something's definitely happened here. Watch closely as I put another one on. And kind of record your observations. All right? If you say anything about energy, you have to show me how you know. What is visible here that you know there's energy going on? What are some of the things we can measure? We can see what's happening as we add more masses to that. How much data would you need to figure that out? We have to be careful not to overstretch the springs. So make sure you put a little note for yourself that you might want to test out the big washers and the small washers when you get a spring to make sure that it doesn't seem like it's going to stretch too much when you put all the washers on there. Remember not to pull the springs too hard because they can get damaged. This is a qualitative lab with some measurement. We should be able to see some kind of trend. So remember, a spring, what can you measure about the spring? What's changing about the spring that you can measure? And how is that changing? And how is that related to energy? You'll be getting your lab journal ready. You'll need 2 pages, a left side and a right side available. Label it Energy Lab Part 1, Washers on a Spring. On the left-hand side, you'll just need some room for your data tables and a graph. Leave more room for the graph. On the right-hand side, you'll leave a section for the purpose and some observations, and you can split the observations in 2, ones where you're sharing with your classmates and ones that you are making yourself. And underneath that is energy's role with the system schema, a written description, pie charts, and an LOL diagram. Please have this ready before you start your lab.